Today is going to be our AWS Big Data workshop. So instead of doing big data work on a localized cluster on a locally hosted cluster, we're going to be doing it on the Amazon cloud systems. So without any further ado, let us look into the agenda. So in the agenda today, firstly, we're going to be discussing what is big data, a brief introduction to big data for those of you who are not familiar with the platform, with the subject, basically what big data is, what's the criteria for big data and all of that. So a brief introduction to that. And then the technologies we use to tackle big data, which are Hadoop and Spark. So a brief intro to Hadoop and a brief intro to Spark. Then we're going to move on to Elastic MapReduce, which is the Amazon cloud solution for Hadoop and Spark. So basically the substitute for using these technologies in a localized environment, we can use it on the cloud. And then eventually we're going to get to the live hands-on demonstration of how to implement big data on the cloud. So firstly, what is big data? So there are essentially 5 criteria that need to be satisfied in order for data to be termed as big data. So those 5 criteria are velocity, volume, variety, veracity, and value. So let me explain these briefly one by one. So the data should have velocity, which means the data should be coming in to your data center or your hard drive at a very high speed, which means it could be on a day basis, it could be on an hour basis, it could be on a minute basis, right? So for instance, say how much data Google's servers actually store in a day from their basically search results. Depending on the number of people searching for things on Google, a lot of data is generated undoubtedly on Google servers every day. So that accounts for velocity. This much data per day. So this data is in the figures of petabytes, basically in Google's servers. So petabytes of data are generated on Google's hard drives every day. So that accounts for velocity. The data is coming at a really high speed. So if this criteria satisfies, so one of the criteria is now satisfied for big data. Then volume. So speed is another thing, but we also need to have volume. So that means the data should be extremely large in nature. So anywhere from multiples of terabytes to petabytes, it qualifies for the volume criteria as well. That means the data is high in volume. So that is the second V of big data. That's basically qualified for when we're actually taking big data into account. And then we have variety, which means the data more often than not will not come from the same source or will not be of the same type. So say you might have a combination of various categories of data. So say for example, from some source you might be getting some MP3 data, or from some another source you might be getting some CSV data. So in real world terms, this is the kind of data that you would be getting when you're dealing with big data problems. Essentially, you will not be getting some same sort of data from every side. You will be getting a variety of data from heterogeneous sources and not homogeneous sources. And then we have veracity. Now, veracity is a very real world term. Basically, it means that the data that you will get in a real world scenario, say if you're working for Amazon, if you're working for Amazon Big Data Analytics, their section, the data that you will be getting will often have inconsistencies present in it, will often have noise present in it, right? So it is also the job of a big data developer slash analyst to actually clean that data, off of its inconsistencies and errors and noise that it has. So the data will have some problems with it because it's a practical case, it's not an ideal case. So that accounts for veracity. And then value. So it's also the job of a big data developer or an analyst to only take information from the data sets that it's receiving that is of value, right? So say if you're analyzing some academic data, right? So a lot of columns would be present in your academic data, such as a roll number, unique identification numbers, and all of that. So those are primary keys, and that sort of data we don't really need when we're analyzing big data, because what are we going to do with primary keys? How does it help us in our analysis? So it needs to be absolutely clear that the data that is coming in should be something, for example, like the grade of the student. like the grade or the percentage and all of these things, or what subjects that student has taken. So all of this data is of value, but say something like their roll numbers or their unique identification numbers, those columns are not of value. So that does not qualify for big data, but something like grades or percentages does. So that is value. So these 5 criteria need to be satisfied in order for normal data to be termed as big data, right? So all of these 5 criteria. So an intro to Hadoop. So we have big data. So obviously we cannot solve this big data problem with normal technologies like Python. Say example, if you're from a data science / data analyst background, you might be familiar with Python. So Python has libraries like pandas and numpy. So all of that help us basically to implement data analytics and data science, so to speak. But that is not the case for big data. What happens with big data is that your Python and pandas doesn't have the libraries to basically implement this large amount of data at such a high velocity or in real time in our data analytics models. So we need some additional technologies. We need some frameworks on top of which we can run Python, right? So that our big data storage and processing problems are handled. So there comes Hadoop. So, say for example, if we were implementing normal data analytics, that is a normal use case for just one computer device. You have your data, you have your small 2 MB data set, and you put it into your Python. You import it into your Python Jupyter notebook, and then you perform your data analytics on it. So that is possible on just one computer device, not a big task, right? But say if you have petabytes of data, right, constantly coming in from your data source. So what will you do then? You need a technology that is able to efficiently store all of this data coming in, and you need a technology that is efficiently able to enable parallel processing on that data. So there Hadoop comes in. Hadoop is a framework that helps us create a cluster of nodes. So these nodes are normal devices that you have or laying all around, office like devices, and you connect them all together in a network. And Hadoop, when you install Hadoop on these devices, it creates a cluster, right? So we will get into that. So this is first discuss Hadoop first. So the Hadoop helps us to process big data in parallel. It is made up of a distributed file system called HDFS and a computational layer called MapReduce. So Hadoop stores data using the HDFS, and Hadoop processes data using the MapReduce framework. And Hadoop is open source. So if you're looking to change some parameters in Hadoop, or you're looking to implement your own particular use case using this technology, you can do that because it's open source. Documentation is available. You can change and tweak according to your needs. So let us look at the architecture. So what happens is you have a combination of multiple nodes, multiple devices all connected together with Hadoop installed. Say you, and this creates a server, this creates a cluster server. When you upload a big file on this cluster, that file is divided into parts and it's equally distributed in all of these nodes. So you are not storing a petabytes of information on only one node. You're dividing the petabyte of information into multiple blocks, as many blocks as required, and you're storing it on the various nodes present on your cluster. So this helps you store things very easily because you're not putting it on one device. Even if that device doesn't have petabytes of storage, it will still store a small amount, and the rest of it will go to the other data nodes, right? So that is how you store things. And then what happens is the data is also replicated. So these blocks that you're storing on these data nodes, they are also replicated across one or depending on the replication factor that you put in, it will be stored on 3 4 other nodes as well. So this also ensures that if say one data node fails, right, one data node goes bad, your data will not be lost. Your data will still be there. It will just be recovered from another node. So this is what happens when you upload data to your Hadoop cluster, and that is the architecture for that. So we have our name node, which is our metadata storing node, and we have our data node, which actually stores the data in the form of blocks. So when you upload data, the name node basically points to the start mark of that data and the end mark of that data. It stores that information. The name node is a small device. It doesn't have to be very highly hardware intense. basically, so to speak, because the name node only stores the starting points and end points of the data, that information, and it basically controls all of the data nodes together. So you don't actually store anything on the name node. You store things on the data node. So when the file gets uploaded, it gets divided into equal parts on the data nodes and gets replicated depending on the replication factor. And when you want to download this file, when you want to read this file, you basically do the same procedure. You contact the name node. The name node gives you the information as to where the data is available on the data nodes, and then all of that is coordinated by Hadoop itself. The data, all of the blocks are combined, and then the combined view is given to you when you read it from a client. So that is how the architecture, the HDFS, which is the Hadoop distributed file system, that architecture works. So this is managed by Hadoop, and this essentially solves the big data storage problem. Only the storage part is being solved by HDFS. So let me look at if any doubts have been accumulated now. All right, so an intro to Spark. So Hadoop was the first technology that came in to solve the big data problem. But eventually, as time went on, we needed new technologies that are faster in nature. And as memory, your RAM, basically your random access memory, it was very expensive in the beginning. So that is why we used to use Hadoop. And I'll explain to you what that means. So let's get into Spark first. Spark is an open source framework. Again, if you want to tweak the software, you can tweak it because it's open source. It has been developed for cluster-based computing. So your combination of multiple nodes combined into a cluster. So that sort of computing, the big data computing, it's optimized for that. It was originally developed as an upgrade to Hadoop's MapReduce framework for big data analytics, right? So Hadoop used a MapReduce framework on top of its HDFS to execute any jobs on the data present in the HDFS in parallel. So all of the nodes will execute their respective blocks. Say a petabyte of data is divided into 3 blocks across 3 nodes. So the processor on all of these 3 nodes will execute their respective blocks, and that way we are able to achieve our use case, achieve our job completion in a very less amount of time. It achieves data parallelism. That is what MapReduce achieved. But the problem with MapReduce was that every time we had to store data, or say if we are calculating data, calculating any sort of job, if we're doing any sort of job, and we are creating some intermediate information, if we are creating some intermediate data, the data was stored on the disk, which means the hard drive space of the respective node that the job is being executed on the disk, right? So the problem with storing any intermediate data on the disk is that you are not there is an input output delay every time you want to call that data back, right? If you want to re-import that data back into the job, there is an input output delay. So this is what MapReduce was based on. Say there was an intermediate, you were analyzing petabytes of data, there was an intermediate phase where you had to store this data in an array, right? So that array basically was not stored in the random access memory. If it was such an extremely large amount of data, it was stored on the disk, your hard drive space. And then it took some more time to re-import that data back when the second phase of the job began, like the reduction part, say, for example. And that is basically increasing the time in which we are getting our desired outputs after input output delays. So this was MapReduce. So then came an Apache Spark. So this was the time Apache Spark came in at a time when RAM as a commodity became really cheap. Memory as a commodity in general became really cheap. So now we could afford storing these large amounts of data on our RAM itself rather than putting them back onto the disk. So the intermediate data that is generated while running a Spark job is stored in the RAM. So there is virtually zero input output delay when we access that data back or run any other jobs on that data. So this achieves a much faster output. So it's about 100 times faster. So depending on the data size that we have, just the advantage of Spark is that it can get about 100 times faster in nature than a normal Hadoop job. So that is why Spark is a much more popular language, not a language, a framework that we use today for big data analysis. But obviously, for the understanding the basics of big data analysis and big data technologies, you need to understand MapReduce. But in real world use cases, we use Apache Spark. So then comes in Elastic MapReduce on AWS. So the problem that we get when we're dealing with localized servers, say in an office space that we have. So we have a client, say you're sitting somewhere else, right? In the office, you're sitting even remotely somewhere else, like you're sitting in another part of the country, but you have remote access to your office. Office's local network, right? And you have, in turn, you have your remote access to your big data cluster present within your office, right? So you can have remote access to that, or you can be sitting in your office and have remote access to your big data cluster, right? So this is the traditional way of implementing big data, a combination of devices, right here, a big data cluster, and we remote access and we run our jobs on it. So the problem with this is there are certain disadvantages. So say you don't want to run a big data job all the time on your cluster. You don't want to be doing that. But if you rent or buy hardware, if you are basically spending electricity bill, if you're basically spending some money on your electricity bill that is running this cluster all the time, 24/7, just from an electronic device standpoint, right? You're incurring costs that you don't need, because you don't need to be running your cluster at that time. And then on top of that, you need a server administrator, you need a big data Hadoop administrator who's going to be coordinating all of these devices together, who's going to be adding new nodes to your cluster or scaling down your cluster and removing new nodes, applying security patches, software upgrades, and if any new software has to be installed on top of your framework, or if your framework has to be upgraded, you have your administrator doing all of that. So you have to pay your administrator as well. You basically, the only support that you have is from your own technical team. You need to pay your technical team for the maintenance of that big data cluster, right? So all of these are the cons, because you have to incur the cost of all of that. You have to manage it all on your own. But the easier option, if you don't need immediately, if you don't need a very high cluster, if you don't need a really big cluster, the immediate solution for that would be to use a cloud architecture. In a cloud architecture, what you'll get, like AWS, is this architecture. So you have your remote access to your AWS console, which contain all of your big data services, your AWS big data services, and then your console, your Amazon account is connected to the cluster that you would create, right? So what happens in Amazon is, when you create a Hadoop, when you create this cluster, an EMR cluster, an Elastic MapReduce cluster, what happens is Amazon instances, a lot of Amazon instances, depending on the number that you've set in, those amount of instances start up, right? And they self-install Hadoop, they self-install Spark, depending on what softwares you've set in to install. And the cluster is created automatically. You can set up auto scaling as well. So in auto scaling, what happens is, if your job is of a high requirement, the cluster will scale up automatically. A new nodes would be added to your cluster automatically. If your job is of a lower requirement, nodes would be removed from your cluster automatically to reduce your billing costs. So all of this are the advantages that you get with this AWS cloud service. You don't even have to pay a maintenance team. You don't have to pay a Hadoop server administrator. You don't have to do all of that. Amazon will handle it for you, and Amazon will also provide customer support. So if you're facing any difficulties, you can simply contact customer support, because it's a paid service, and they will resolve your query or your doubt, or solve the problem for you itself. So abstract visibility, you don't need to directly deal with the Hadoop cluster. That is not your job. You don't see the cluster in its actuality. You only interact with the console, and you only interact with the master node of the cluster that you're creating. You don't need to deal with the data nodes. If you want, you can, but you absolutely don't need to. The scaling up, the installation of softwares, all of that will be handled by Amazon itself. So these are the advantages of cloud services. Lower costs, no maintenance team, no Hadoop administrator, and it's very flexible. You only have to pay for the services that you use. If you're not using your cluster, you won't be charged. So I already have my account set up. I'll just go to that this moment. So this is what you will get, right? If you create an AWS account, a cloud account, this is what you would get on Amazon. Once you head into the console, nothing complex about that. A normal website, right? You have your account set up, all of it set up. And then when you click on this search bar that you have over here, you can see this. So it has a lot of services. So you have a service for virtually everything that you can imagine, with regards to web technologies, with regards to application building, with regards to data analysis, search engine optimizations, machine learning, artificial intelligence, storage. If you need a storage solution, if you want to store some data somewhere, you can do that. So a lot of services are there basically, right? What happens is the first thing that you have is EC2, right? This is the most basic thing that you will ever hear about in Amazon. Amazon Web Services. So EC2 is basically virtual machines. Virtual machines means that Amazon has their data centers in their localized locations, wherever they have in the US or in Mumbai or in Singapore or wherever the server locations are. So you have these regions also. So these are the regions where you would have your server locations. Amazon has their data centers over here, right? So any location, whatever is the closest to you, you'll select, or yeah, you'll select that, and then you can create instances. So in those data centers, you will basically reserve a spot when you create an instance. For the amount of time that you created the instance, you will reserve that spot, and you can do with that reserved server space, with that reserved server processing element, you can basically implement your jobs on the cloud itself without actually having to use your local computer for that. So I won't have to use the resources present on my Windows system to actually execute the jobs, but I'll just use the virtual machine on the Amazon data centers. So when you go to instances, right, you have the option. It takes some time to load. Yeah, so you have the option of launching an instance. So you have all of these operating systems available. You can install the Amazon Linux on it. You can install RHEL, which is another Linux operating system. You have your Ubuntu, you have your Microsoft Windows Server and all that, right? So you'll basically select how many instances you want, or you'll select if you want to launch one instance, and you'll basically launch it, and you'll be able to connect to it and run your jobs on it. So what if we go back and go to EMR, right, which is Elastic MapReduce. So what EMR will do for you when you go to create cluster, you can basically, I'll first name my cluster something. So let me call this live workshop. And then you can enable logging. So all of the log information with regards to the cluster will be stored, right? And then you can select one of these pre-installed packages that not pre-installed, basically an option of what sort of softwares and frameworks you want on your cluster. So you can select Hadoop, Hive, Hue, Pig, and Taze, and all of this. You can select that. This is the core Hadoop setup. If you want Spark on your cluster, you can select this one, which has Spark 2.4.5 installed on it, and Hadoop and Yarn. So this is the bare minimum that you would need for Spark. If you're looking for other options and specifically looking to select what you want to install, you can go to advanced options. So here you will be able to select all of the big data technologies that you would need for your particular use case. So this gives you a more customizable way to actually do that. So I'll just go back to quick options because I wouldn't be needing Hive or Pig or anything. So I'll just select Spark, right? Because we're going to be implementing, as an example, we're going to be implementing Spark today. And then you can, once you've selected the softwares that you want to install, you can go to your hardware configuration. So earlier, right now, I was showing you EC2 instances, right, which were single instances. So what this EMR option will give to you is an option to select the sort of device type, the machine type that you want for your instances. So these contain the hardware specifications. So I'll just select the default, which is the M5.X large. This is not free tier, by the way. So if you create this instance, depending on the amount of time you use it, a certain amount of money will be cut, but not that much. And you can select the number of nodes that you want on your cluster, right? So we can select one. If we select three, that would give us one master node and two core nodes, which are the slave nodes or the data nodes, basically, right? And the master node is basically the name node. You get that. And if we select 4, it will basically change to one master node and 3 core nodes. And if we select 5, it will basically change to one master node and 4 core nodes. We'll select 3 for the moment. right? Even though we don't need three, I'll just start three just for demonstration purposes. And then you can enable or disable cluster scaling. So as we discussed in the PowerPoint presentation, cluster scaling basically means if the job is requiring a high amount of resources, your cluster will scale up. And if the job is basically needing a low amount of resources, your cluster will scale down. That means the amount of core nodes will go up or go down, and your price will be you will save some money. You wouldn't have to pay for a reserved amount of clusters all the time, because in a lot of cases with these big companies, it's always better to save that money rather than have an amount of clusters, or have an amount of nodes always reserved. And you can also set a minimum amount of clusters that you want it to go to, and you can set a maximum. So at the maximum of loads, it will at max go to 4 nodes, and at the minimum it will go to 2. But we don't need scaling right now. And then you can select a key pair. So let me just, this is a key pair used to connect to your name node. I'll show you how. So to learn how to create a key node, and you can go to your EC2 console. And as you go to your EC2 console, you can go to key pairs. So this basically helps us connect to the name node. So it's basically an authentication thing, related to the security features that Amazon provides to you, so that nobody else other than you is able to connect to your cluster. So let me create a new key pair for this workshop. Let's call this workshop. Let's call this EMR, right? And let's download the PPK file for this and create the key pair. So it gives me an option to download it. So I've downloaded it. So I can use this private key that I have to basically authenticate to my cluster. And eventually, after I've selected that new key that I just created, which is this, if you can see it, workshop underscore EMR, workshop underscore EMR, it already shows. Click on that and then create your cluster. I think it should be started now. Yeah, it's running, right? So you can simply click on clusters, and I'll see that it's running. So we have our waiting cluster ready, so we can run our jobs on it now. So it's called my cluster because I didn't change the name. You can change the name to anything that you would like, right? So if I click on it again, so this is the page I was earlier on, right? So now I want to connect to it, right? So I will simply click on connect to the master node using SSH. So these are the options that are given to me. So if I want to currently connect to it, I will just use this. This is the host name. We'll copy that and go to my session, paste it over here, right? So this is the host name of my master node, right? The port remains 22 because that is the SSH port. Go to a authentication and browse to your recently created file. So let me see where I've created it. So if I do this, I should be able to see it. Workshop EMR. If I simply, where is it located? Oh, it's located in my D drive. Just a moment. Selected that. So I have selected it in my D drive, and I'll click on open. And that will instantly, when I click on yes, it will instantly authenticate me. I don't have to enter any password. I don't have to log into my account. It instantly authenticates me into my MapReduce, not MapReduce, into my master node, right? So as you can see, this Linux machine is running Amazon Linux 2, right? So this is the operating system that is by default used, this EC2 instance, right? It's an EC2 instance and the master node, and it's running Amazon Linux 2, right? With Hadoop and HDFS and Spark and Yarn installed. So all of that is already installed. So the first thing that I would do is I want to analyze some file. So I have this data set already on my desktop, right? Just a moment. If I go to my desktop over here, I have this data set, which is the yellow data set, yellow.csv to be precise. If I open it up, I can see, just a moment, it takes some time to load. So there is some data available in it. Just expand this for a moment. So there's some data available in it, right? We have we have this taxi trip data basically. So it's a cab service like Ola, like Uber, like Ride or any taxi app that you get, right? So you have your trip distance. If I just expand this, you have your trip distance. You have your the locations, the coordinates of your pickup, right? You have a rating. You have your I have other information as well. We're not going to be dealing with that. We're dealing with this amount of data that we are dealing with right now. So you have your fare amount, you have your extra, you have your MTA tax, you have your trip amount, you have your tolls amount. All of this is present there for every trip, basically. So we'll take this data and perform some analysis on it. So say if this data was really large, like petabytes in nature, so it would have been appropriate to use our clusters for it. So we are connected to our EC2 instance. So we'll leave it for now. We'll minimize it. So what I want to do now is upload that data to an online source. So how do I do that? Amazon also provides us with storage services. So if you type in S3 and go to S3, open up that service. So this lets you create buckets and you can upload some data on it, right? So that you can access it online. So I'll create a bucket, right? I'll call this bucket workshop. The region would be, okay, it cannot contain an underscore. Just remove that. EMR, type in at the end of it. The region would be Asia Pacific, Mumbai. And I'll just copy some existing settings from some of the other, yeah. So I'll just click on next, right? And this is not important to manipulate with. No need to get into that. Click on next, and we will not be blocking public access because we're going to be accessing it from our EMR cluster. So we will not be accessing, we will not be blocking any access. I'll acknowledge the settings, and then I'll simply click on next and create the bucket. So once I've created the bucket, I have this over here. I'll open that bucket up, right? So I'll create a folder within this bucket. I'll call this taxi data, taxi something. I'll just call this taxi and create the folder. Just a moment. Save it. Yeah. So I have this folder here. So what I'll do now, I'll open up the folder. I'll upload my yellow.csv. So I'll go to desktop, find my yellow.csv, click on it, and then click on upload. So I now have it in my bucket on an online service. So what I need to do now is simply click on this and copy the path. So that is done. We have our data available to us, the link to it available, and we'll go to our cluster now, right? So just to just a moment. Yeah, so this is the location, how it looks like, right? So this is in the format of S3. So the extension is S3 right here, and you'll get the folder location and everything. The first thing that we would do is start our Spark job. So type in Spark -shell. So this will start up Spark on the cluster that we've just created, a session basically, and we'll be able to use Spark commands now with Scala. Yeah, so let me continue now. Let me look at any doubts that I've accumulated. So let us now create the job. So the first thing that I would do is create a variable. So I can store this taxi data in, right? I need to create an object to store my taxi data in. So the way it happens in Spark is you create RDDs. So RDDs are resilient data sets, and they are basically objects, Java JVM based objects that store your data in the RAM. So in your random access memory. So when you create that, Spark dot read, then you specify a format. So my format is CSV dot option. You can say whether you want to include the headers. So I want to include the headers. So headers are the column names. So you pass in the value as true. Option, you want to have this data set as a schema. So you will turn on in first schema. And then you want to add in the replication element to it. So if in case of any hardware failure, you want to add the option of fail fast. So the mode would be fail fast. And then you would simply add in the location. So after you've added, you set in the load command, you can add in the location. So location for my case is in the double quotes. I will simply, okay, just a moment. I'll have to copy this again. So go to your S3 and go to your particular bucket, not this one. Back to CMR, taxi, click on this, copy the path, paste it over here, and close this up and press enter. So what that will do is it will take some time to fetch that data, but it will eventually create the RDD out of that data. So you'll have your resilient data set created out of that data. So right now we can see our data frame has been created out of that. So the RDD has been converted into a data frame. And if I simply type in df.show, I want to see 5 records out of this or 4 records out of this and press enter for a little bit of expansion. Just a moment. Yeah, and I press enter. So I can see that it's been sort of imported in a table format. Just a moment. I think there's an issue with the column names. I might have missed out on a particular column. Yeah, so the issue was, just a moment. I'll just bring this back up again. So the issue was why the headers are in C1, C0 format is because I typed in headers instead of header. So I'll just create another data frame called df1, and it will basically do the same thing, except this time we will have our headers in the column name. I'm sorry, are you guys able to hear me right now? Yeah, some people are saying that they're not. Okay, everybody is able to hear me then. Okay, fine. Yeah, so the issue was earlier I had typed in headers instead of header, and that is why my headers were in the actual columns instead of the column names. Now, if I simply type in df1.show something like 2, then I can see that now the column names are the header names, right? So that is what I wanted. So now I can simply use these column names in order to perform my queries, right? So now the data importing part is complete. We've done that, right? And we now have the advantage. Say if we were dealing with petabytes of data right now, it would have been the exact same way, right? You don't have to do anything different. You would just have to specify the online location of that data, and you would have to start up a Spark shell. You would have to take that address and create a data frame out of this, and all of the intricacies involved with dividing that data, storing it on various nodes, and basically importing it into the RAM. All of it would have been done by Spark and Hadoop on its own in the background. So that is the advantage of using these frameworks when you're dealing with big data, right? It might seem similar right now to what you would do with the Python data frames and whatnot, but with Python data frames, you cannot possibly import such a large amount of data, and you cannot possibly process such a large amount of data on one device. So this helps you coordinate all of that and execute all of that. So now let us implement some SQL with this, right? So how would you go about that? So firstly, I will not call this df1. I will call this something different. So let us call this df1, and we want to create a view out of this. Create or replace temp view. So this is the temporary view that I'm creating for this session only, and we will call this taxi data. So I can refer to this table as taxi data from now on and press enter. So this will be more convenient for us when we invoke our SQL clause. So we are not actually required to install SQL on this. For those of you who are wondering, we don't need to have an SQL server for this. Spark imitates SQL. Spark has an SQL engine built in. It will imitate SQL, right? But you cannot use Spark as a database. You cannot do that. Spark only imitates SQL as sort of a data warehousing tool, and you can store the outputs that you create, but you cannot use it in an actual SQL server. So once we've done that, we will use spark.sql. So say my first question, my company manager asks me this question. So the data team has provided me with the data. So I have imported that data into my Spark terminal. I'm a big data analyst. So my head asks me this question. My manager asked me this question. So your task is find out the number of trips that have been taken all throughout this month, or however long the data set is, for however long the data is for, right? So naturally, what I would do in that case is type and select, and then I would type in count and put in an asterisk over there from taxi data, and close the SQL statement and type in dot show, because I want to see the output for this. So this is something that you might be familiar with. This part, select count from taxi data. This is exact word to word SQL, right? Exact word to word SQL. So you can see how easy it is for somebody who's coming not from, say, a development background, not from, say, a Python background, even or data science or data analytics background, to get into this, right? You just need to learn up until here. That is the new thing that you need to learn. And after that, you simply are implementing SQL statements. If you're using Spark SQL, not other Spark elements, if you're simply using Spark SQL, but you're now able to query the data that is basically satisfying the criteria for big data. So you can see how easy it is to get into big data with this. The entry point is low. You can get into it, right? So you can just simply do that and press enter, and wait for some time for it to analyze all of that. So as we can see, we waited for some time, the data loaded, and we can see that the count is about 10,000. So it basically means that the number of records that are present in the data sets that I have uploaded, they are 10,000. So there we have only have 10,000 records, right? So that is basically what I meant by number of trips, right? So there are 10,000 trips for which the data is available in the data set. So this is a basic question, right? Any particular doubts up until now? Rajat is asking, can we use quantum computing to deal with big data? Definitely, but Amazon will not give you quantum computing instances. Amazon definitely is working on quantum computing, so is Google, so is Facebook. But the technology is pretty expensive for now. And if they're using it for their big data or AI or ML model creation needs, they're doing it in their own office space. But yeah, definitely it can be used. Any sort of processing element can be used to analyze big data. In fact, if you use quantum computing for big data, it will drastically increase your throughput, drastically increase the time in which you were able to execute your jobs. Okay. So the next thing would be, let us know something like what, say, what is the total revenue that is generated? Your boss asks you, what is the total revenue that is generated out of all of the trips? So what would you do in that case? You will look at the column names, right? So if you want to calculate the revenue, you simply look at the column that is saying total amount. So that is basically corresponding to your revenue, right? Total amount. So what you want to do is add all of the values present in this column. So we are now in SQL territory. If I simply bring the previous statement up, right? So what I want to do now is change this count to sum. And I want to change the column name from asterisk to total underscore amount, which is total underscore amount. Close this up, and when I press and dot show, take some time. We'll evaluate all of the 10,000 records. So the good thing about this is, by the way, right now it's taking this much time to calculate for 10,000 records, right? The good thing about this is, even if you're dealing with, if you have a large enough cluster, even if you're dealing with petabytes of data, it will still take the same time. So you can see the extreme advantage that you would get with Spark in this case, right? It will still take the same time, even if you are dealing with, say, billions of records, right? So you can understand the advantages that you're getting with that. So with 10,000 records, you might not see this time as a big deal. You might think that my computer would be able to solve that in the same amount of time as well. But your computer will not be able to solve that in for a petabyte amount of data in the same time, basically. A question is being asked. Do we need to use Spark on AWS, or we can download it like Jupyter or Python? So Spark is definitely a framework that you can download, but it has certain dependencies. So you cannot simply download Spark on Windows and start working with it. You need to install certain Hadoop utilities for that, because Spark requires that. It is a dependency of Spark. But it's not definitely not recommended on Windows computers. You can use Linux systems are better suited for Spark, definitely. Yeah, you don't have to use AWS for Spark. You can also install it on your local systems and create a cluster in your own home or in your own office. You can do that as well. Is there any restriction to the format of data that can be fed to Spark? No, there is no restriction at all. The data does not have to be structured. So there are also elements to Spark like Spark ML. So in that case, you can simply import unstructured data. You can the job of a data analyst is basically to big data analyst is to clean that data, convert it into a structured format so that it can be used and so that some value can be added to it. So you have it is your job to do that. So definitely Spark can create an RDD out of any data basically, and it is your job to basically provide some structure to it and then perform your queries or your use case on it. Okay, so let's continue now. So say another example that we can take up is what is the average of the trip amount? So I can bring the statement up, and similar to what SQL functions are available to you, you can simply type in AVG. So that is the function for average, and we can look at the column that we need to refer to. So we want to calculate the average of the what? Trip amount. So where's the trip amount that we have, right? We have tip amount over here. We have fare amount. So let us calculate this huge total amount for that. We do not need to concern ourselves with that. So we see what the average is. Press enter. Okay, a question is being asked, can you create scripts in Spark and automate them to execute? Yes, definitely you can. So right now what I'm doing is I'm running the sort of a Jupyter notebook sort of a way where I'm running Spark. I'm running a Scala terminal for Spark, right? So I'm able to execute one statement after another. This is convenient for me because I'm sort of running, I don't want to execute a lot of statements as one. I want to show you guys what I'm doing, right? One by one step by step. But you can definitely create a Scala file. You can import your Spark libraries into the Scala file and write the exact same statements that like I'm writing over here. You can create your main function, write the exact same statements, and execute them, and not execute them. Create a script out of it. .scala file, and you can create a cron job in your Linux cluster is running. It will do that 11 a.m. every morning, or you can that is how it works basically. You can run that script periodically as well. So, all right. So, say if I take in another example, I want to calculate a fraction. So, say spark.sql, I want to calculate the fraction of the total. I want to calculate this moment. I want to go over here and look at this. So, there's a tolls amount. So, this is what you would get on tolls, on road tolls, these checkpoints and all. You have to pay a certain road tax for that. Those are the toll amounts, and you have your total amount. So your boss wants you to calculate how much does the cab driver have to pay as a fraction out of the total amount to the road tax, right? So let us calculate that fraction. Select, and then I will simply type in sum tolls amount. So this is the total amount, and I'll divide this by some total amount. Double quotes close and press enter dot show. Okay, some error I put in there, just a moment. Okay, I didn't close the bracket. So I can see that it's about 1.5% or 0.015 fraction. This is the percentage of the total revenue that is going to road tax. So your boss now knows it. Your boss is now happy, basically. What are the other? Is there? Does Spark work with every database? Uh, So what you're doing right now, you're not actually the data that I imported is not from a database. It's not from some sort of a relational database or a NoSQL database. It's actually a file. What I had was a .csv file that could have been as big as terabytes in nature or petabytes in nature, but right now it was 2 MBs, but it could have been terabytes in nature. And I imported that. Firstly, I uploaded it to an online source. That was a step that just to integrate the S3 service with this, just to show you guys how to integrate various AWS services together. So I imported it into my S3 bucket, and then I provided the link for that data to my Spark session, and then I was able to import that data. So that is what I did. So I wasn't actually getting that data from some sort of an SQL database. I wasn't doing that. So let us look at some other examples. Let us look at. So what I want to do now is actually I want to display the some details for each of the payment type. So let's now look at the table. So there are various payment types available. This is the payment type column. So this could be these are coded, right? So this could be 2, 1, 3, and 4. So these could correlate to online payment or cash payment or card payment and all of that. So that's not necessary, but you just only need to look at the numbers that all of those payment types are corresponding to, right? And we simply want to categorize that data for each payment type. We want to calculate the average fare generated for each of the payment type. So let us do that. Let us calculate the average fare that is generated for each payment type. So type in spark.sql, select payment type, and get the average of the fare amount as average fare. So I want to also give this an alias so that it doesn't show like what happens is you will get this in your output. But if you want to actually assign an alias to it, you can simply name an alias by using the as command, fare. So simply type in from taxi data. And I want to group this by the payment type. So I'll get the average fare amount for each of the payment types that are available in the data set. So as we can see now, for payment type 1, the average fare is 13 point whatever. For payment type 3, we have this. For payment type 4, we have this. For payment type 2, we have this. So as you can see how easy it gets in time. Oracle and SQL Server data files are in encrypted format. We cannot we cannot read directly from the database. But yes, your query is correct. We can convert the data present in our SQL tables into CSV or text format, and then we can use it in our Spark, definitely. Can we join multiple DFs? Yeah. So there are multiple ways to join DFs. So you can use the normal Spark SQL to actually join your data frames, or you can simply create your data frames and use the native Scala commands with Spark to actually do that. So those are possible. You can definitely perform all kinds of joins, like full joins, left joins, and all of those things. You can do that. Let me calculate the average trip distance. So to that spark.sql. Let me look at the column which says trip distance. So it's trip underscore distance. And we can simply type in. So we have our average trip distance as well. It's about 3 miles or 3 kilometers, whatever the unit has been used in this particular data set. So those are some examples of what you can do with Spark. So definitely this is one way of implementing Spark, right? This is with Scala, and we are implementing SQL, which we are implementing Spark SQL. But there are ways to do this exact thing with data frames, inbuilt data frames with Scala. There's a way to do these exact things with Python as well. You can do this with Python as well. There are libraries available for Python. There are libraries available for Scala. There are libraries available for R programming. So you can integrate Spark with any of those three technologies and perform your big data needs. There are libraries also available for Java also. So you can do that with Java as well. All of this basically. So it depends. So if you're coming from an SQL background, you can use Spark SQL. If you want to implement more complex models with it, which are discussed in the course, you can use PySpark for that, and so on and so forth, basically. So if you want to look at the pricing, I think some attendee had a doubt with the pricing just a moment. Look at the pricing. of the clusters. So yeah, so pricing for Amazon EMR and Amazon EC2 on demand, right? So let's look at that. So these are the general purpose machines that we were talking about. So I think I was using this one, right? M5 2X large. So it's about 0.384 dollars per hour, and this is when you're actually using it, right? So this is per instance. By the way, this is per instance. It's not per the cluster. And depending on how many instances you have, right? Depending on how many instances you actually added to your particular cluster, so it will multiply accordingly. So let me look at this. So at an average, depending on the use case that you may have, if you're simply keeping it dormant, it will cost you $0.096 per hour, basically, for my for your practice purposes. You can minimize that as well if you're simply doing your practice and simply terminating the cluster. So yeah, some doubts have come in. Yeah, so there's doubts about the notebook, the Jupyter notebook. Just a moment. Yeah, so you can go simply when you are opened up with the page that you have, you can simply click on notebooks, right? And you can create a notebook. So let me simply type in practice notebook, right? And Spark. Choose a cluster that you've created, which is my cluster in my case, right? And default security role, that will work. I think this should work. Just a moment. And then simply create notebook. So that is how easy it is to actually create a notebook on top of the cluster that you've just used. So it'll take some time. And once the notebook has started, you can actually open it up and it'll open up in your web browser. So if I simply click on open in Jupyter, so it'll create it'll basically give me the UI for the Jupyter notebooks. So now I have my IPYNB. So this is something that you might be familiar with if you're coming from a Python background. So simply, if I create new and click on Python 3, so I have all of these options over here, very neatly organized. So if I click on PySpark, right? So which is what we would want to use normally. Without any hassles, without any setup, you have your terminal and you can type in your PySpark commands in this. So I'm not actually familiar with PySpark commands. I have done my big data in Scala, but the course content is, if you're choosing for the PySpark, you can get your content in PySpark, and if you're choosing for Scala, you can get your content in Scala. So you can execute this one by one, and you can use PySpark commands for it, which are virtually not very different from Scala commands, but some syntax error, not much. Some syntax difference, not much. Okay, so that is basically to demonstrate how easy it is, and you can simply you just try some Python code. Print one, and just simply click on play. So it'll start the Spark application first. So this wouldn't have happened if say we weren't dealing with PySpark, but since we're dealing with PySpark, that is why it's happening. So once that has started, it'll actually print one. So yeah, all of that. So let us just check back on the notebook. So as we can see, it took some time for the PySpark session to start. So the session is available as Spark, right? And we actually printed our one. So we just printed the one, but yeah. So there are commands for PySpark as well, which are very similar to what I just did over here, right? Very similar to that. I think it works the same way as what we would do. But the advantage with using Python is that you can use the other libraries that are available in Python and integrate them with your Spark. So say you have your libraries such as matplotlib and whatnot. You can use that with the data that is available to you with Apache Spark, right? And then obviously you have Spark mlib. So you have Spark machine learning libraries. So that help you create machine learning models using Python with Apache Spark. So big data machine learning essentially. So yeah, so the advantages, let us go again once again. So with notebooks, you also get the option to choose a Git repository and pre-import the code that you would need. So these are the features that Amazon so gracefully provides to you, because all of this has to be done manually when you're doing it with a base Linux EC2 instance, or you're doing it with a localized Hadoop cluster, or a big data cluster in general. You have to get the code, you have to clone it, and then you have to use it, right? So you have to do all of that. But you can see how easy it is. The UI that is provided to you by Amazon Web Services, you can get all of the information and the code from the start, and you simply implement the use case that you have very easily. So these are the advantages basically you get. And this is Amazon QuickSight. So if I go to QuickSight, not AWS QuickSight, it's QuickSight. If I go to that, yeah. So it'll ask you to create an account and stuff, but then you can simply create a new analysis. Say if you want to take some of these sample data sets that you have. So it gives you the information for that. You can create your analysis. So this is one of the sample analysis that QuickSight already has, but you can also add a source to this. So say if I add two particular columns to the visualization that we're creating, right? So it does that very easily as well. So this is the comprehensive data visualization tool that AWS provides to you. So say if you've created some sort of an output out of your Spark analysis right over here, right? You can simply give the data information, the location over here, and it will basically create the visualization for you. So I'll simply go back now. So yeah. So thank you for attending, guys. That is about the end of the session. Yeah, I'll be seeing you guys again next time. Goodbye from Intellipaat.